Good morning, dear, and welcome back. So, you have started watching videos on Introduction to Machine Learning, and today we are going to discuss a very important topic in machine learning, that is regression analysis model. So, first of all, what is regression analysis and how to develop a model based on regression analysis? These are the things you will learn in this lecture. So as you know, machine learning is all about data, right? So first, you will have to have data for which you are trying to make a model. Okay. And regression in machine learning paradigm, there are two types of problems. One is called regression problem. What is regression problem? Say I have a feature X, okay, and I have the output corresponding to this feature, which is denoted by Y. Then, if for each X we have a Y, each X we have a Y, then we are trying to figure out the relation between X and Y is called a regression problem. I can take an example. Say now just world is recovering from COVID. So suppose X is a feature, it's a time series data I have, it's a day, right? We are collecting number of infection so this data we are collecting. So world meter is there, anybody can go to the website and then you can collect data, right? Say each day I have this many infections, okay, and these are the ground truth. Means for x1 this is y1, x2 y2. You understand, right? So this is day and this is y-axis is number of infection. Or it could be anything actually. Say this feature denotes the house floor area. So we are trying to make a regression analysis between the size of the house and its cost. So you'll have to have real data for that. Okay, from real estate business you can collect data. Okay, in the assignments we will give you lots of such real data. Without real data, no regression analysis, no machine learning model can be developed. Okay, so say X is one feature. It could be floor area, and Y is the cost of the house. So it is linear relation. The more floor area, more costly house would be. So these assumptions are there. And another assumption is for each size of the floor, you have a different price, which is not correct. But this assumption has to be there to make a regression analysis. Because what I am trying to mean is, say you have 8 square feet. For that, the real ground truth is say $500,000 US. Okay, nowadays housing prices are very costly, and then regression analysis demands that okay, for 801 we should have a price which is different from the earlier one, which is not the case, of course, but still vaguely we assume that X and Y are continuum. Means for each X you have a Y. The data is such. Okay, so this is a regression problem. And another problem is, you see, for a bandwidth of X, if you have a particular discrete Y, so for example, which is actually the case, okay, so say a housing price, so 700 square feet to 900 square feet, if the value or price of the house is same, so then this is not a regression problem, it's called classification problem. Okay, when for a bandwidth of feature, you have a discrete output or y. Output here is a price. Okay. So if you are developing an app where you will somebody will put floor area, I need this floor area, and your app should be able to tell that, okay, what could be the price of that house of that floor area. So you understand? So if for a bandwidth of x, y is discrete, then it's a classification problem. Say you are trying to classify tumor, whether it is benign or malignant. Okay, if a tumor, the assumption is if the tumor is malignant, it will be big. Okay, and tumor size say is x, then there is some bandwidth. Big means between x1 and x2 size. If the size is beyond something, you classify as a malignant. If it is less than something, you classify as a benign, means harmless. Okay, so this is a classification problem. So I understand it's the beginning of the class, so we will continue our discussion. I understand that, okay, at least you have understood what is regression problem and what is classification problem. Okay. One more thing is very important, that you have some data, you have collected real data or ground truth data. Our assumption is the data with which we are making model, and this model will be used for predicting the environment afterwards for different data, and those data also has similar distribution. So throughout the machine learning, this assumption we make. Okay, so this is generalization, but this assumption may not be true. But to be our machine learning model effective, this has to be there. Means if you are making, what I mean is you are making model with some kind of data, and you are trying to predict an environment where the data trained is completely different, then this model will fail. For example, in India, the initial COVID phase, right, the say 2020 March, so 5th March, 6 months, 6th March, 7th March, so entire March month's data I have of 2020, and I have infection, number of infection, right? And then I made a model, regression analysis, through regression analysis, which we are going to learn. And then we are trying to predict with that model the very unfortunate second wave which hit India 2021, May, June. So this model will fail because the data trained, the data distribution with which you made model is different. So then why we'll make a model at all? This is very important because it may happen in many problems if you have a trained, and for quite some time the train of the data remains same. Okay, and so regression analysis can give you answer for once a model is developed for data beyond model, and will predict correctly. And this is very important. In industry, this is heavily used. So many things we have talked about linear regression, many other things we will talk. So now let us see, if you have data, real data, that is x, y, then how to develop a model using regression analysis. First of all, as I said, you will have to divide the data into two parts, training and testing. Because testing for any model development, how good or bad, is a design, right? It's not a, with the help of mathematical analysis, we are trying to design. Still, it is a design problem, means you require your intuition, seeing the data, what kind of model you will fit. So once you are designing some model, somebody else are designing some model on the same data set, you need to test. If testing, through testing you figure out that your model performance is better than others, then your model will stand. So normally, whatever data we have, say 500 data we have, so 70% of 500 data means day, 500 days, and infection, number of infection, or size of the house, price of the house, all kind of thing, right? In stock market, price of a particular company, stock, okay, a particular company, date, so time series, these are time series data. Day by day, what is the price of a particular company, okay? Y is the price and is the day. So, and you want to make a model which will predict that how the particular company is performing, and based on that you can make your decision on investment. If the company is not performing well, is like this, so you are not going to invest. If it is like this, you are going to invest, because with the day you can expect high return. Anyway, so this is a design, and suppose I have collected some data. These are example, okay? So I have lots of data, okay? And this data, so this is my so-called, you can, training zone, and suppose there are some other data here, okay, and here also, okay, that also I have collected, and I will use them for testing. And suppose I see, it looks, the train of the data, from the train of the data, it looks like the relation between x and y is linear. So theoretically, this is theoretical y, or I denote it h, which is a function of x parameterized by w. W is my parameter of the model, and those parameters I need to determine, okay? So I seeing the train of the data, I decide that this will be my model, a linear line, okay? So W0 x0 plus W1 x. So x0 in machine learning, you will see, is called, always we normally put x0 equal to 1, and another name it has, it is called fictitious feature, and the parameter which is attached with the fictitious feature is known as bias, okay? And why we put bias and all in the machine learning course, we will reveal all these things, okay? So for better generalization, we need to put bias. So putting x0 equal to 1, I have this. So this is my model. So ground truth is y, and theoretical truth according to my design is hx parameters by w, which has two, in this particular example, which has two parameters which are yet unknown to me, w0 and w1. Is it clear? Now let us consider that we have m number of samples. So we can just denote in a generalized way x sub I, comma y sub I, that is for each x I have an y, each x I have an y. I have collected this down to I equals to 1, 2, 3 for m. We rather in machine learning, also in subsequent discussion, we will use this notation. They are the same. X prefix I, y prefix I. Okay, I equals to sample 1, 2, 3, m number of samples. If it's housing price, if you have 500 data, m will be 500. If you have 1000 data, m will have 1000. Okay, and where each feature is a vector actually, but for plotting it in a 2D, I am calling it a particular feature, say size of the house, which is floor area, and this is the price. So my assumption is too simplistic, that housing price only depends on floor area. we are learning how to develop linear regression model, right? How to develop model using linear regression analysis. That's why we are making so much simplification. But this simplification model development technique will be valid for any complicated model development. For example, if you are having several features, so we call multiple regression analysis, it will be exactly the same, only notation, vector notation we will use, but the idea, the technique will be remaining same. So let us try to understand first the basic simple model. So you have developed a model, and what is your objective? Somehow to know the parameters of the model. Okay. So for that, what you need, very intuitive. Okay. I need an objective function. Okay. So you see, objective function. What could be objective function? The common sense is error function. Why error? Because you see, I have my theoretical design and I have ground truth. For example, for any x, say x1, this is x1, I have a y1 value. This is real. So this is the data I have collected. But my model is telling, no, for this x1, you have this y theoretical or h. So this is the real value. This is the predicted value, not real value. Real value is this, and this is the predicted value predicted by my model, which whimsically I have designed. Okay. So you are incurring in doing that, unless they are the same, you are incurring some error. And what is the error? Error is actually theoretical value, means what your model is predicting, and what is the ground truth. So difference between them is called error. So if, look carefully, so intuitively, if I have an error function now, where an error function is very intuitive. What is that error function? I have designed something, and my design or predictor, now we will call it predictor. Whatever I have designed is a predictor. Corresponding to x value, some x value, my design is predicting some value. And corresponding to that same x value, I have some ground truth, actual y value. So the difference between them is error. And if somehow in that error, you see, this is error. This is error. The difference between my predicted and ground truth. Now, somehow I have injected in this error, I am calling it error function, two parameters which I need to figure out. These are yet to unknown, right? W0 and W1. So I have injected in this error function, and now I have squared it. Why? Just right now, you see, for some x, my y is this, and theoretical y or h is this. So this is the error. Okay. And for some say some x2, I have this is ground truth. This is y. Okay. This x2, and this is my predicted value. This is h, wx. Okay. So here, the difference between h, wx and y was positive, isn't it? Because h1 was bigger than actual ground truth. Here, actual or ground truth is bigger than your predicted value. So for x2, this is negative. So you see, sometime the predicted value is more than the ground truth. Sometime predicted value is less than the ground truth, right? And I have a generalized line in between, and we are not actually, so this is not the curve fitting. I cannot use a predictor which is passing through all these points. Why? You will learn that afterwards, because that will be very bad, because my objective is not to figure out the functional train of the data for which I am developing model. It has to predict beyond the data which is used for design. For that, I need a generalized line like this, and which will pass through ground truth value, which is something will be above, something will be below, so that it will generalize well. Okay. So what you are observing is sometimes in doing so, sometimes the error is positive, sometimes the error is negative. So what to do? Just to have a good function, you square them up. Right now you assume that we are doing, although we will learn in my next lecture, it has bigger significance of doing that square. But right now you can just assume that we want error. So it's a function, right? It could be error function, simple. It could be square error function. J is actually square error function. Okay. You are clear? So the reason I make square right now is because sometimes my predicted value is more than the ground truth. Sometimes my predicted value is less than the ground truth. And now what I am trying to do, you see, for each sample, I will try to write the function. You see, for each sample, x1, y1. So my predicted value is w0 plus w1 x1 minus, so this is theoretical, minus ground truth, that's square, plus, because summation is there, for this sample number 1, sample number 2, same thing, right? w0 plus w1 x2 minus y fx2 square, all kind of things. For each sample, you are able to calculate this error. Okay, say error 1, error 2, and they are all positive. So you have this function now, and I am calling that function a multivalued function j w0 w1, which contains my parameters. And your objective is now how to minimize that error, right? So if you can minimize that error, then your predicted value and ground truth error will be smaller and smaller. So you have a best design. And in doing so, we will take the help of calculus, okay? Because we are learning a non-iterative method, and when you have less number of features, you have not so huge data, why we should use iterative method? They are bad, isn't it? Bad in the sense, computationally, they are more time consuming. So computational complexity is there. But in case of non-iterative method, constant computation complexity. So we want, first if possible, non-iterative method for linear regression analysis, model development, okay? So our objective function is this. I have a function, and inside that function I have injected my unknowns of the parameter w0, w1, and with the help of calculus, 12 class, that you have a function of 2 variables. So you need to differentiate this function, 12 class or first year of engineering. So differentiate this function. To minimize, we need to differentiate this function and making it to 0, right? So if you just now see, this is x, so you have a function, say, so what you do, this is partial differentiation because you have several variables, here 2, it could be many, that will be equals to, if x square is there, that will be equals to 2x, right? So here you see, just differentiate. 2 is coming over here. First, I am differentiating with respect to w0. So 2 is coming over here, and to x is here, this, which is remains. And then you are differentiating with respect to, so would be 1, right? So that's why simple differentiation is yielding. You take a notebook and you try also, okay, to differentiate this function first with respect to W0, and which is yielding this, and make it to 0. And who will be here? 1 or 2? 1, right? Is it clear? So you assume that x is 2x, right? You just apply method of substitution and you are smart in doing calculus, very easy, right? So you will get this when you are differentiating this function with respect to W0 and make it to 0, because that is calculus, right? So if you want to figure out optimum value of a function, you differentiate that function with respect to the variable, make it to 0, double differentiate it. If it is positive, then minimum, if negative, maximum, like that, okay? So here we are assuming that if somebody do second derivative, minimum means you will get positive value, but we will not do that. We are optimizing, okay? Making it to 0 is good enough, we believe. So you are getting this, and then you see what you can collect. Now simplify it. For each sample, this is the values. So 2 cancels out because divide by 2, 0 divided by 2, 0. Now W0, how many W0s you have? For each sample you have 1. So you have m number of samples, 1, 2, 3, 4, m. So m times W0 plus W1. You see here W1 is coming out, and the W1 is attached with each sample times x. So x1, x2, x3, with every xi, I have a W1. So W1 can be taken out, which is a constant for this expression, and summation of x prefix I equals to 1 to n, minus, you see, no W here, y I equals to 1 to m equals to 0. So this is one equation, and the moment you have the samples, right? So this, just like this, you can calculate. This very easily you can calculate. So m, you know, say I have 500 samples, 100 samples, 1000 samples. For that, everything is known except W0 and W1. So you have got a equation, linear equation in W, and making it to 0, right? So this is how you have developed. And then another variable you have, W1, whose value is yet not known to you. So you differentiate, again differentiation. Now you differentiate this with respect to W1. So as it is, so again, so differentiate x squared with respect to x will be equal to 2x. So this x is coming over here, and then you will have to differentiate this with this inside with respect to W1. So xi will be there, so xi. So multiplied by xi, right? So this multiplication. Clear? So you have to differentiate this same function with respect to W1, and you are getting this, and then again simplify. So W0 comes out, you see, W0 into x1, W0 into x2, W0 into xm. So for every sample W0 is there, and then you have to, as a multiplier it is there, so you'll have to take it out and sum them up, xi. Then W1 xi squared, xi, you see, x1 into x1, x2 into x2, so xi squared, blah, 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 minus, I have it in class, minus x into y, xi into yi. So after simplification, you are getting another equation. So these two equations you have got by partially differentiating the function with respect to the variables. Here parameters of the variable, because your design is not complete yet. Okay. So That's very simple. So you have formulated an error function, and you have differentiated that function with respect to as many variables are there in your predictor or in your design, and you have um, developed that many linear equations, and we know how to solve them, which I will discuss. I will start from here in my next lecture, and since this is very important and interesting things to know, I am going into minute details, and we'll talk about how to solve these equations and make a model based on linear regression. Till then, stay safe, have a nice day, bye bye.